continue. So, class, we have been studying the concept of group theory. Okay, we saw in the some like 2 lectures back, we saw what are the main motivations behind it. Like, if I consider at least the computer science field itself, the main ideas behind the field of cryptography lie in this group theory, right? And besides computer science, there are numerous other application domains where these are relevant. Okay, now before we delved into what is group and all, we studied various operations of various properties of binary operations. We saw the closure property, which means basically that given you put an input as an ordered pair from a given set A, the when you apply the binary operation, the output should also be part of the set A. Then we saw the associative property. uh, then we saw commutative property, and then the identity property. Okay, existence of identity property basically means an element belonging to the same set, which when multiplied by any element gives back the element itself, right? So if such an element exists, it's known as identity exists. Similarly, you have an inverse, wherein if you multiply any element with the inverse, you get the identity element back. Then we had idempotent and distributivity law. So idempotent was basically a special case wherein any element multiplied by itself gives back the element. Okay, so in this case, we saw how if you satisfy idempotent property, then your identity and inverse were the element itself, right? And then we have the distributive property, uh, and finally the cancellation property. Now, based on all these properties, different algebraic structures were defined. Okay, so first of all, what was an algebraic structure? Algebraic structure or algebraic system is defined by two things. One is a non-empty set on which you define the various operations, and second is your binary operation. Okay, so any algebraic system that you're going to study today or what you have studied yesterday will always be defined by these two things: a non-empty set from which you will take inputs and from which you will get an output, and a binary operation which you're going to apply. So what we start with the smallest or the simplest most kind of algebraic structure, which is called a semi-group. Okay, so if you have an algebraic system A star, it's said to be semi-group if it satisfies two properties. One is the closure property, okay, which you already know what it means, and other is the associative property. So if you satisfy closure and associative property under this operation for this given non-empty set, such an algebraic system is known as semi-group, right? And then there were some sub examples of it, so I'll skip that. So that was your semi group, which had the property of closure and associative. Okay, now if you add the third property of existence of identity element to it, then such a structure is called monoid. Okay, so if you have just the two properties, it's known as semi group. If in addition you have the identity property, it's together called a monoid. Okay, so basically every monoid is necessarily a semigroup already because it satisfies the first two properties, right? After monoid, we saw what is known as group. Okay, so group basically has these three properties: associativity, identity, and inverse. So closure is by default there. So I had skipped it yesterday because closure automatically comes into the picture whenever we talk about any binary operation. Okay, so if you look at monoid, which is closure, associative, and identity, if you add the inverse property to it, it becomes a group. Okay, so what is the hierarchy? You have closure property, you have associative property, you have identity property, and you have existence of inverse property. Okay, now if we just quickly summarize, if I have first two properties, what kind of algebraic structure is that, class? If I have the first two properties, closure and associative, right, what kind of structure is it? Very good, it is a semi group, right? I assume everyone knows what these properties are because we had extensively discussed it with the examples. Now, if I consider closure, associative, and identity, then what kind of algebraic system it is? Very good, a monoid. And finally, if I have all the four properties, then it is known as a group. Okay, and group is the main structure over which the entire group theory is based. Okay, so apart from having these properties, to closure, associative, identity, and inverse, there are various other properties also which groups satisfy. Okay, which you can show with very simple proofs. What are those properties? First property is, as you say, it's a group, so identity exists. But the specific property of group is that the identity element, if it exists, it's going to be unique. Okay, so there are no multiple identities for a group. There's going to be a unique identity. Okay, similarly, if it's a group, that means it satisfies inverse property. There are not multiple inverses, but the inverse element is also unique. Okay, similarly, if you have a group G, then for any element A in G, if you take the inverse of inverse, it will give you the element back. Okay, similarly, if you take the inverse of A B whole inverse, it will be B inverse A inverse. Okay, and the last property which groups hold is are the left and right cancellation laws. Okay, so these were some of the properties we saw of the groups. Then we saw what is a finite and infinite group. Okay, depending on which set you define a group, if that is finite, then the group is called finite group, and if the set on which you define the group is infinite, then it's called infinite group. Okay, the last thing we had studied yesterday was called the order of group, which basically tells you how many elements are there in a group. Okay, and we had argued that if you have a group of order 1, then the only element present in it will be identity element. Okay, why is it so? Because for a particular algebraic system to be a group, it necessarily needs to have an identity as well as inverse. Right? Now, if it has just one element, so definitely that one element is the identity element. Okay, and what can you say about its inverse? If I have a group of order 1 which has just one element, what can you say about its inverse? What is its inverse? Yes, anyone? What can you say about its inverse? Very good. It is E only, right? Because there's just one element. So identity is same as inverse, is same as any other element. That is E. Okay. So this is where we had ended up our discussion yesterday. So we'll build upon the same discussion today, and we'll start with a new kind of algebraic structure called an abelian group. Okay, so let us see what is an abelian group. Any questions till this point? So this was just the recap of yesterday's lecture. Any questions till this point? Yes, class? Okay. So now what we are going to do, we are going to study some more algebraic structures. Okay. But one thing you need to remember is there's nothing new concept going to come in today's lecture. Okay. So if you have understood what are the properties, you're just going to rearrange different properties, and based on them you're going to define various structures. Okay, like you can see the first structure for today, which is called abelian group. Okay, so let's see, when do we call an algebraic system an abelian group? Let us consider an algebraic system G with a binary operation star. Okay, this system is said to be an abelian group if it satisfies first 1 to 4 all the group properties. Okay, what are those 4 properties? Closure, associative, identity, and inverse. Okay, which means for a abelian group, for any algebraic system to be an abelian group, first it should be a group itself. Okay, so whenever you are given an algebraic system and you want to show that it's an abelian group, first thing you need to show is that it's a group itself. That means it satisfies the properties of closure, associativity, existence of identity, existence of inverse. Okay, then what is the additional property? The additional property which makes a group an abelian group is the commutative property. Okay, so if for the given operation you are also commutative, such kinds of groups are known as abelian groups. Okay, so abelian groups, the abelian name comes from the fact that group is there, which comes from the fact that you have the first 4 properties. Okay, but if you are an abelian group, then you also need to have the commutative property. Okay, so you can see the hierarchy: semi group, monoid group, and now abelian group. Moving ahead, the next algebraic structure we have is known as a subgroup. Okay, so let us see what is a subgroup. If you consider a non-empty subset H of group G, okay, remember G is basically a set. Okay, if you consider a subset of G, say H, and and you say that a non-empty subset H of a group is itself a group. Under the operation of G, we say H is a subgroup of G. Okay, so what do I mean? So suppose I have a set G, and under the operation star, it is a group. Okay, that means it satisfies all those four properties. Now, if I consider a subset of G, say H, a non-empty subset of G, and I consider H on the same operation, same as the operation of G. Okay, if this also forms a group, this group has a special name called subgroup. Okay, where sub comes from the fact that it's a subset. All right. So, when you have a subset H of a group G, this is said to be a subgroup if it satisfies the following properties. One, it is closed under the operation of G. That means if A, B belong to H, the operation of A and B also belongs to H. Second, there is an existence of the what you say the inverses, and there's existence of the identity element. Okay, generally you will see whether it is sub semi group, whether it is subgroup, you only skip the associative property. Okay, so if you go down the slides, when we were studying semi group, when we studied a sub semi group, you would recall that what you considered there was the closure property only, right? So whenever you skip this associative property, usually you come under the domain of sub. Okay, sub semi group or subgroup. Okay, so when do you say generally algebraic system is a subgroup? If it is based on a set H, which is a subset of another set on which the group is based. Okay, so subgroups necessarily need a group for its definition. Okay, so if you have a set G defined on a binary operation star defined as a group, okay, and then you extract a subset from it which satisfies all the properties of a group except the associativity, that's not necessary, then such a subset is said to form a subgroup of G. Okay. Is this clear? What is a subgroup? What is a abelian group? As a general terminology, you should remember, like, mostly when you use this term sub instead of in place of anything, sub monoid, sub semi group, subgroup, you usually tend to skip the associative property. Okay. Okay. Now let's move ahead to some more algebraic structures. So this group theory is just about remembering which properties are there. Okay. Main conceptual thing here is just the properties. If you know the properties, then you understand this module. Okay, now let's see some more different kinds of groups and subgroups. So if you consider again a group based on set G, okay, a specific kind of a group is known as a cyclic group. Okay, and a specific element in this group is known as the generator of group. If you have the property that there exists an element X in that group such that every element of G can be written or form the power of that element. Okay, let me repeat what is a cyclic group. So suppose you have a group defined on the set G and a binary operation star. Okay, now this group is said to be a cyclic group if it satisfies the following property. What is the property? The property is that there should exist some element X in G such that all the elements A in G should be expressed as some form of this generator element. Okay, so this element from which you generate all the elements is known as your generator element. Okay, like I can give you a best example of a cyclic group. If you consider the set to be 1 minus 1 iota and minus iota, okay, the imaginary square root minus 1 number, and you consider it under the operation of multiplication, it is also a cyclic group. Okay, how is it cyclic group? If you consider iota uh, and different powers, you will generate all the other members of this group. So you can see if I raise I raised power 1, right? So I have I back. If I do I square, what is it equal to? Remember, iota is your square root minus 1, right? It's minus 1. If you do I cube, it is I into minus 1, which is minus I, right? And if you do I4, you have minus 1 into minus 1, which is 1. So you can see all the elements of your this set can be generated from I, right? So in this case, we say that the group is cyclic. Okay, so when do we say a group is cyclic? If there is some element in that group which can generate all other elements. Okay, and such an element is known as generator element. Like you can see in this example, I is your generator element. Okay, is this clear? What is a cyclic group? Similarly, you can have cyclic subgroup also. Okay, the only difference is that this G, instead of being a group, is a subgroup. Okay, so that is where we call the element X to be the generator element, and we denote it by this symbol. Okay, is this clear? What is a cyclic group? Okay, so cyclic group, the main property it holds is that if you consider any elements in that set, you can generate them by the given set. Sorry, the given element. Okay, if there is any group which satisfies this property, then such groups are known as cyclic groups, and that element which generates all the elements is known as the generator element. Okay. All right, so let me, before I move ahead, let me see if you understand it properly. If I give you this group and I give you the operation star, is this a cyclic group? And if it is, what is its generator? It is a cyclic group. Why? Because I can write all of them as power of a, where a is your generator, right? A to the power 1 is a to the power 2 is a square, a to the power 3 is a3, and so on. Okay, and how do I get 1? A to the power 0 is 1, right? Now suppose I add 0 to it. Is this a cyclic group? Why? Why is it not a cyclic group? It's not a cyclic group because 0 cannot be written or expressed as power of a. Okay, so for cyclic group, it is necessary that all the elements of that set should be generated by some power of that element. Okay, is this clear? Now cyclic group and the corresponding cyclic subgroup, is this clear to everyone? Yes, you can argue when a group is cyclic and when it's not a non-cyclic. Yes, class, is it clear to everyone? Okay, great. All right. So let us move to the next important part of this group theory, which is known as cosets. Okay, let's try to see the formal definition of cosets and let's try to understand what it means. So let H be a subgroup of group G. Okay, what does this mean? Let's revisit the definition. When do we say H is a subgroup of G? Okay, when we have a group G defined on an operation and we take a subset of G, which is H, and the H also forms a group under the same operation, right? That is, it satisfies the closure, identity, and inverse properties. Okay, then we say H is a subgroup of G. Okay, so now if you know what is a subgroup and you assume that H is a subgroup, now how do we define a coset? A left coset of H in G is basically subset of all the elements which can be expressed as X, H, okay, such that X, H belongs to your set H, okay, and X belongs to G. Okay, so what is basically left coset? You take the subset H and you append, or you add a prefix to it, some elements which are belong to the larger set G. Okay, so such kind of set is known as your left coset if you prefix the elements. Okay, If you postfix the elements, that means you apply them on the right hand side like this, then this is known as your right coset. Okay, so this is under the multiplication operation. If you consider under the addition operation, then left coset is if you add this x element before, and right coset is if you add the x element after. Okay, so those sets which are generated after prefixing or postfixing elements from the generator, the main set, those sets are known as the left and right cosets of a given group. Okay, let me give you an example to understand it better. So suppose G is my say a square 1 a square a cube, and H is a subset of it. It is suppose 1 and a. Okay, now suppose I choose x to be a square. Okay, can you tell me what are the values of xh under the multiplication operation? Can you tell me the values of xh? What is the set xh? This is known as your left coset. Can you tell me what is the left coset? I fix x to be a square, that is one of the elements from G. Okay, and this is my h. Excellent. I'll just simply pre-multiply all the elements of h by x. So you a square into 1 is a square into 1 is a cube. So this set is known as left coset. Okay. Similarly, if I have to make a right coset of it, since multiplication is commutative, so hx will be equal to xh. It will be equal to a square a cube. Okay. Is that clear? Ravi, is this clear? How do you generate left and right cosets? What you need to do, two things you need to do. You need to have a subgroup and you need to choose an element x from the main set. Okay. Then to get the left coset, you pre-multiply that chosen element to the entire subset on the left. And for right coset, you post multiply it. Not just multiply, any binary operation on which you have defined. Okay. Can everyone generate a left and right coset? Does everyone understand how to generate it? See, this module is going to be, a collection of very small topics. So if you are stuck at any place, please let me know. Is this clear? Can everyone generate a left and right coset if you are given these information? Okay. So before I jump ahead, let's ask you a question and see if you have understood it properly or not. Now you know that H is a subgroup, okay, and G is a group, okay. Suppose I tell you that H and G both have abelian property. What can you say about the left and right coset? Okay, let me repeat the question. Suppose I give you, this is not an proven fact, okay, but I am giving you an assumption that suppose both an H and G are abelian. Okay, I assume everyone knows what is an abelian property, right? Then can you make any claim about left and right coset? They would be same, they would be different. Because in general, they could be different, right? Because you're pre-multiplying and post-multiplying things. But if I tell you that H and G are abelian, which means it's commutative, then what can you say about left and right coset? Exactly, they will always be the same. Why? Because if they are abelian, means the operation is commutative. So if you take x into h or h into x, it's going to be the same, right? So if xh is equal to hx, means left and right coset are equal. Okay, is that clear to everyone? So if you have abelian property or the commutative property, then your left and right cosets will boil down to the same set. Like you can see here, since multiplication operation was commutative, you can see the left and right coset were exactly same. Is that clear to everyone? How they are going to be the same? Yes, class. Is this clear so far? Okay, so far what we have seen, we started with abelian group. Okay, then we saw something called subgroup. Okay, now we saw how to generate different kinds of sets from subgroup, which are known as cosets. Okay, So let us move ahead now. Okay, now we move to something for which I already gave you motivation, with abelian property. Okay, so the next thing we have now is a normal subgroup. Okay, so there was something called subgroup. Now there is something called normal subgroup. Okay, so if you recall what was a subgroup, subgroup had identity, inverse, and closure. Okay, now let us see what is this normal subgroup. Okay, so given you have a group G, okay, that means defined on set G, and suppose H is the subgroup of G. Okay, this subgroup is said to be a normal subgroup of G if for all the elements H in H. Okay, so for all the elements H in H and X in G, your X, H, X inverse also belongs to H. Okay, then it is said to be a normal subgroup. Okay, so what is a normal subgroup? It's not a very simple property, but what we need is product of our element from G and its inverse with a special element from the subset H. If that quantity also belongs to the set H, then it is said to be a normal subgroup. Okay, so basically what we are saying is, for every element X in G, if X capital H X inverse, that is set of all the elements with X H X inverse, is said to be normal if and only if X H inverse is also a subset of H. Okay, subset and equal actually. Okay, now if you have an abelian group, you can easily show that every subgroup of H is a normal group. Okay, that is what I had mentioned in the last slide. Okay, let us see if this is true. First of all, when do we need a subgroup to be normal? For any subgroup to be normal, we need that for all the elements H in this subset H and the elements X in G, any element of this form X, H and X inverse should also be in H. Okay, so it's like if you pre-multiply the elements of this set with some element along with its inverse, then that should also be in H. Okay, now what we are claiming in this statement is, this theorem is that if G is, your group is abelian, then this will always hold. Okay, and let us see why. If you consider any H in H and any X in G, X H inverse, okay, so suppose I just parenthesize it like this, okay. If it is a abelian group, then which property does it hold? Yes, class, if it's an abelian group, so what is the specific property other than the group properties? Very good, commutative property, right? So that means if I have written X H X inverse, can I write it as X inverse H? I just flipped the order of these two. Can I write it like this? Because it's an abelian group, I can, right? Now, if I combine X and X inverse, what is it equal to? If I multiply an element with its inverse, what is that equal to? Remember the property? Very good. It is the identity element E. Okay. And if any identity element is multiplied by any element, what is that equal to? The element itself. Okay, so let me just annotate the properties. So here you use the commutative property, here you use the identity property, sorry, inverse property, and here you use the identity property. Okay, so you can see, if you check what is X H X inverse equal to, it's equal to H only, right? And we know H belongs to H, and that is what we required. If any H belongs to H and X belongs to G, then X H X inverse should also belong to H. Okay, and you can see H also belongs to H, so H is a normal subgroup. But how did we achieve that? You can see at the first step itself, we required commutative property, and for commutative property, the group had to be an abelian group. Okay, so is this clear? What is a normal subgroup and how an abelian group ensures that every subgroup is basically normal? Yes, class, is this clear? Okay. All right, so let us move ahead. So let us move ahead with some more definitions. So before I come to this very important theorem called Lagrange's theorem, let us recall what is your order of group. So I'll just go back a slide so that I'll see you all remember. What do we say is order of group? Yes, class, we discussed this. What is an order of group? Very good. The number of elements in a group is known as the order of group. And we know that if the number of elements is finite, the group is finite. Otherwise, it is infinite. Okay, so that is order of group. Now, there is something also called order of the element of group. Okay, so it's not the order or size of the entire group, but order of a specific element. Okay, which is sometimes also called the period length or period. So what is the order of that element of a group? Basically, order of an element of a group is basically the order of the subgroup which is generated by that element. Okay, what does it mean? Suppose I have a group G and it has elements say A and A square. If I pick an element say A, okay, and I generate a subgroup from this element, okay, the size of that subgroup is known as order of the element. Okay, so what is order of element? Order of element is the order of the subgroup generated by that element. Okay, like I can give you an example. If we consider the group operation to be multiplication, then order of an element A of a group is the smallest positive integer m such that A to the power m is equal to the identity of that group. Okay, if you have such a power which exists such that its power will give you the identity, then you say that the order of the element is m. And if there is no such m such that its power gives you the identity element, then you say its order is infinite. Okay, why you say its order is infinite? Because that means that the subgroup which is generated by that element will have infinite elements. Okay, so what is order of an element of group? It is simply the order of the subgroup generated by that element. Okay, and what do I mean by generated? Generated means that if you take the operation, binary operation defined, all other elements can be represented using that element. Okay, so we have order of the group and we have order of the element of group. Okay, now let's see what Lagrange's theorem say. It actually is going to relate the two. Okay, what Lagrange's theorem states that for any subgroup H of a finite group, okay, this is important, being finite, the order of subgroup divides the order of group. Okay, what it means is that whatever is the size of H, it is a divisor of G. Okay, so I'll give you an example. So suppose G is your A square, A cube, A4. Okay, and H is your A square. Okay, so you can see size of G is 4, size of H is 2. Okay, and you can see that 2 divides 4. So this is what Lagrange's theorem says. Okay, Lagrange's theorem says that your order of subgroup divides the order of group. Okay, it's a divisor, it's a perfect divisor of the group. Okay, this is a fact. Okay, people have proven this theorem that whenever you define a subgroup from a given group, then their order will divide. The order of the subgroup will always divide the order of the group. Okay, is that clear? Is that clear, class? So this slide actually relates you the order of a group and order of a subgroup generated from that group. Okay, is that clear where this example what we are talking about? See, what we mean is we cannot have something like this. Size of G is 4 and size of H is 3. Then it will not be a subgroup. It will not be satisfying the subgroup property. Okay, for Lagrange's theorem states that any subgroup of H will be a divisor of the order of the main group. Okay, do you understand that? Yes, class, is this clear? So like you might have a question like why is it relevant? Okay, this is relevant because this is also telling you how different properties are very much related to the order of group. Okay, so you can see when you have something as a divisor of other element, you see a direct relation. Okay, so you can take multiple powers of a given element to generate the given set. Okay, but if this relation fails, the properties will also start failing one by one. Okay, that's like an intuitive picture of why Lagrange theorem holds. Okay, is that clear, class? What is Lagrange theorem? Class, say yes or no. Like, we have a couple of small topics to cover. So is this clear? Okay, great. Okay, let us move ahead to some concepts of called homomorphism, isomorphism, and automorphism. Okay, all of these concepts you have studied in graph theory. Okay, same concepts are there, only difference is now instead of applying them on graphs, you are going to apply them on groups. Okay, so let us see what are all these in context of groups. So a homomorphism, as we already know, it's a mapping from one set to other set. Okay, in graph theory, the two sets were graphs, but here the two sets are groups. Okay, so mapping f from graph G to G prime such that f of x comma y is equal to f of x, f of y. Okay, that means if you consider the input x and y from a given set G, the mapping is going to preserve the group operation. Okay, so if you take the input as the binary operation of x and y, it will be as if same as applying f on x and applying f on y and then performing them the operation. Okay, so in other words, what does this mean, homomorphism? That the function f is going to preserve your binary operation. Okay, preserve, what do you mean by preserve? By preserve, I mean if I apply f function on x and if I apply f function on y, and on this I perform the binary operation, it will be exactly same as performing the binary operation of 2 and then applying f. So applying f does not change the binary operation. If this condition is true, such kind of f is known as a homomorphism. Okay, if you remember in graph theory, what was f preserving? Anyone remembers in a graph theory when we said f is an isomorphism or a homomorphism, what was the relationship that it was preserving in graphs? Yes, class? Like here it is preserving the binary operation. Okay, which means no matter whether you apply binary operation before or on the mapped function, answer is going to be the same. Okay, can anyone recall and tell me what relation was it preserving when you talk of isomorphism or homomorphism in graph theory? Yes, Ayush, can you tell me what does structure denote in graph theory? It was adjacency relationship. Remember? Yes, exactly. Adjacency relationship, right? All the edges, all the nodes which were having edges between them, the mapped versions also had the edges, right? So they were preserving adjacency relationship. Here we are preserving the binary operation. Okay, and we define something called a kernel of homomorphism. Okay, so kernel of homomorphism f from a group G to G dash has an identity E such that the set x in G, f of x equal to E. Okay, so what is kernel basically? Kernel of a homomorphism is basically all the set of nodes such that when you apply function f on that x, it gives you the identity element. Okay, so it's like this. If I have set G and I have set say G prime, okay, and G prime has some element identity element E prime, all such x which are mapped to this E prime, that is known as kernel of homomorphism. Okay, so what you are doing here, you are considering the identity element of one group and the set of all the elements which are mapped to that element, that is known as kernel of isomorphism. Okay, is that clear? What is a kernel of isomorphism? Sorry, the homomorphism. Okay, it is set of all the elements which are mapped to the identity element of the group G prime. Okay, and we know group G prime will have an identity because it's a group, right? And group has identity as well as inverse. Okay, so I know that this lecture is very heavy on terms. There are a lot of terms, but idea wise it's simple. Okay, there's no new idea coming on, it's just rearranging of the same facts. Okay, so because it's a group, we know it has identity. So all the elements of group G which are mapped to this identity, that set is known as kernel of homomorphism. Okay, and then you already know, like, the if I consider all the elements in this domain codomain set, they are known as image set, and similarly the first set is known as domain set. Okay, so that are like usual definitions, but what is important here is to understand what is graph homomorphism. Okay, graph homomorphism is that function which preserves binary operation. That means if you apply binary operation individually on the two values, okay, and then perform the binary operation between them, and if you apply binary operation on 2 and then apply the function, both of them will give the same answer. Okay, and after that we see what is kernel of homomorphism. It's basically set of all the elements which are mapped to the identity element of the other group. Okay, so that is your graph homomorphism. Okay, now let us see what is graph isomorphism. In general, if you are given two algebraic systems, say G1 star and G2O, okay, these systems are said to be isomorphic if there exists an isomorphic mapping F from G1 to G2, okay, such that the following holds. One can be obtained from other just by simply renaming the elements and the operations. Okay, so in general the relation between isomorphism and homomorphism is same. Okay, if you consider it only as a one-to-one function, that means every operation of G1 can be mapped to the operation of G2. Okay, then it is known as your homomorphism. But if you consider the onto relation also, then it becomes isomorphism. Okay, so the relation that we have studied in graph theory between homomorphism and isomorphism, same applies here also. Okay, the difference is on what do you apply it. Okay, in graph theory it was applied on graphs, here we apply them on groups. Okay, that's the difference. Okay, otherwise the idea wise it is same. It is a function which preserves some operation. Okay, there it was adjacency relation, here it is the binary operation. Okay, let's see an example of graph isomorphism. Okay, so there are two functions given. Okay, there are two functions given. There is this cross and there is this square dot. Okay, so A star, like if you do a cross A, it means the answer is A. If you do a cross B, the answer is B. If you do a cross C, the answer is C, and so on. Okay, similarly, if you apply this dot operator, 1 square dot 1 gives you 1, 1 square dot W gives you W, 1 star dot W square gives you W square. Okay, now you have to determine whether these algebraic systems are isomorphic or not. Okay, what you need to do in isomorphic is simply replace the elements of first group by the other, replace the binary operation of one by the other, and the relationship should hold. Okay, what it means, if I suppose map B to W square and I map A to say W and C to 1, so wherever I have a relation from 1 to C, it should hold. Okay, so if I am saying, say A cross A is A and I have mapped A to say W square, so W square into W square should also be equal to W square. Okay, so how do you check something is isomorphic? You simply replace the binary operations with each other and rename the variables under their images and see if the relationship holds. Okay, now for these two functions, can you tell me what is the value of f? So what should be a, what should be f of b, what should be f of c, so that the table holds? Okay, do you understand what table holds, right? A should be mapped to something from 1 w and w star, such that if I perform any operation of a with that, the corresponding operation should also hold in this table. Okay, can you see what could be the possible mapping? So you can see a is here. Oops. Okay, you can see a is here and a is here and a is here. Okay, you can see here you have 1 1 1. So what should you map f of a to? F of a should be 1, because you can see this, it's on the same positions on the table and the relationship will hold. Similarly, f of b should be mapped to w and f of c should be mapped to w square. Okay, since I have a function wherein I can map the elements of group 1 to elements of group 2 and the relationships still hold, so I can say that two of them are structurally same or they are isomorphic. Okay, if there was no possibility, okay, so suppose there was some element d and there was some element say w cube and they didn't hold the same relation, then I would say that they are not isomorphic. Okay, as long as you are able to find a mapping such that the relationship in both of the tables holds, then you say that the given two groups are isomorphic. If it does not hold, then they are not isomorphic. Okay, is this example clear to everyone? Yes, class, is this clear? Okay, so I don't have much time. Okay, finally, the term automorphism. Automorphism is a special case of isomorphism where the two groups are actually equal. Okay, if you show that there are two groups, say G1 star and G2O, between which there is a mapping such that every element of G1 can be mapped to G2. Okay, and it turns out that the G1 and G2 are same, such kind of morphism is known as automorphism. Okay, so basically automorphism is a function from G to G. Okay, a function from a given group to itself. Okay, can you tell me what kind of function would this f be if both of them are same? So basically what I am saying is any element of f, g, say a, is mapped to itself. So can you tell me what function is this f? Very good. It's an identity function. Excellent, Yasir. Because I am mapping every element of group G to itself, right? So f is actually an identity function. Okay. So when your f is an identity function, such kind of morphism is known as automorphism. Okay. The automorphism is basically a special kind of isomorphism where the two groups are actually exactly equal. Okay. No renaming is required because they are exactly equal. Okay. So we have homomorphism, isomorphism and automorphism. Okay, is this clear, the difference between the three and how they are defined on groups? Yes, class, is this clear? See, I'm going relatively fast, but anywhere you're not understanding, please slow me down. Okay, otherwise it doesn't make sense to cover the syllabus if you don't understand. Okay, great. So let us move to now the last algebraic structure, which is known as rings. Okay, now what is a ring? A ring, so let me just quickly revisit what we had studied. We had closure, we had associative, we had identity, we had inverse, and we had commutative. Okay, this was our semi group, this was our monoid, this was our group, and this was our abelian group. Okay, this is the story so far. Okay, now when we come to the rings, another algebraic system. Okay, so suppose R is the group on which it is defined. So ring is always defined on two binary operations instead of one. Okay, so an algebraic system R with addition operation is said to be a ring, okay, with two operations, binary addition and binary multiplication. It's said to be ring if it satisfies the following condition. Okay, what are the conditions? First is that R on addition operation should be an abelian group. Okay, if you consider the set R with the addition operation, it should be an abelian group. That means it should satisfy all these five properties: closure, associative, identity, inverse, commutative. Okay, and if you consider R with the multiplication operation, it should only be a semi group. Okay, it should just satisfy closure and associative property. Okay, and the third and last property it should hold is it should be distributive. The addition should be distributive over the multiplication. So if you satisfy all these properties, R on addition is abelian group, R on multiplication is semi group, and the relation between addition and multiplication is that they are distributive over each other. Such kinds of rings are known as the such kind of structures are known as the rings. Okay, is that clear? What is a ring? As I said, it's all going to be same properties, just some new ones are added. Okay, so I can give you an example of a ring. Like if you consider the set of integers from 0 to 9, 0 to 8, this is basically closed under addition. Okay, if you this is under the operation addition and multiplication modulo 9, it forms a ring. Okay, so if you do a modulo 9 operation, okay, and you define it on this set, you will see it's a closed structure, and it's a ring actually under addition and multiplication. Okay, modulo 9 basically means whatever you divide from this number, the remainders are always going to be from 0 to 8. Okay, so you can check it for yourself. You will see that it satisfies all the properties of being an abelian group under addition, being a semi group under multiplication, as well as being distributed. Okay, so after you have your basic ring, there are various special case of rings. Okay, how are the special cases defined? Special cases are defined for filling up the gaps. Okay, you can see that, let me bring in this chart back. You can see that for addition operation, it satisfies all the five properties. Okay, but for multiplication operation, it satisfies only the first two. Okay, so different types of rings which we have, we'll see most of them will satisfy the remaining properties for multiplication. Okay, so you can see it clearly. What you have is you have already the distributive property, you have all properties holding true for addition. अब जो बाकी कुछ like the remaining one जो भी बची कुची है, identity, inverse and commutative, if you have these properties along with these, then you have various special kinds of rings. Okay, you will see here. Like if your ring satisfies, in addition to all the properties of the ring, the commutative property, it is known as commutative ring. Okay, but under multiplication, because addition one is already contained in this. Okay, if your ring, besides having the ring properties, also satisfies commutative property for multiplication, such rings are known as commutative rings. Okay, if your ring now you have commutative properties covered. Now if your ring has ring properties and as the identity element, okay, it's known as unity ring. Why unity ring? Can anyone recall what is the multiplication property identity element for multiplication? Yes, class? Very good, it's 1. Okay, so if your ring R defined on addition also has a identity element under multiplication operation, such a ring is known as ring with unity. Okay, another special kind of ring is known as ring with zero division. If it's possible to find two elements such that their product is equal to 0. Okay, if you have two elements whose product is equal to 0, then such elements are said to be such ring is said to be a ring with division 0 property. And similarly, opposite of this, okay, if you have an algebraic system R with addition operation and the two binary operations of addition and multiplication, it is said to be ring without divisors of 0 if for any numbers a and b, or any elements a and b in R, we have a b is not equal to 0, implies that none of the two are 0. Okay, if your product is equal to 0, okay, then it is said to be ring with 0 division. And if it is not equal to 0, it's known with the non-division property. Okay, normally for natural numbers, integers and all, you have not 0 division. Okay, as long as the numbers are not 0, you can never have their product as 0. Okay, so these are some of the special kinds of rings which we get by adding certain properties to the already existing properties of your ring algebraic system. Okay, is this clear? So this basically covers your group theory. Okay, is this clear? What is a ring? So you'll have to go through it just once more. I'm just thinking I could give you some example of ring with 0 division. Uh, okay. Can anyone think of spontaneously a ring with 0 division property? It should have some elements which are not single variables, because for single variables you will always have without 0. It should be some compound statement which when you multiply will give you a 0, right? So I think it gets the sum of those elements should become 0 if they are not individually non-zero. Roughly it should be that. I'll see an exact example, I'll give you that. Okay, but is it clear the different subtypes? How do you extract them from the main ring? Yes, class, is that clear? I'll just take some more minutes. Is this clear, class? What is a ring? Okay, so if you recall that table, semi-group, group, monoid, abelian group, ring, that way you can remember this entire group theory. Okay, there's nothing beyond that for this module. Okay, so now coming to the last topic. So this topic is actually from your first module, but it's very closely related to group theory. That's why I wanted to incorporate it here, which is known as lattice. Okay, let us quickly see what is lattice, because it's very closely related to the group theory. If you consider L to be any non-empty set, okay, but closed under two binary operations, meet and the union, the intersection and the union. Okay, and if it satisfies the following laws: the commutative law, the associative law, and the absorption law. Okay, so commutative, associative you already know. Absorption law basically means that if I take a meet over union or a union over meet, the second element inside gets absorbed. Okay, so if any of these sets under these two operations satisfies these three properties, such kind of set is known as a lattice. Okay, and lattice are important because the Hasse diagrams that you studied in the first or second module, that is very closely related to it. Okay, you understand what is a lattice? Very closely related to the group structure. But here the operations are not arithmetic operations. You are dealing with the set operations of intersection and union. Okay, so any set, any non-empty set with these two operations, if it satisfies these three properties, it is known as a lattice. Okay, now any lattice which has an existence of the greatest element, okay, and a least element, such lattice is known as bounded lattice. Okay, so lattice is what? Lattice is any non-empty set with two operations of union and intersection for satisfying the three properties of commutative, associative, and absorption. Okay, now if this lattice has a greatest element and a least element, it is known as bounded lattice. Okay, now suppose I tell you power set of a set S under the operation of intersection and union. Okay, is this a bounded lattice? So let me tell you, it is a lattice because it's going to satisfy all the three properties, right? But is it a bounded lattice? If you say yes, you have to tell me what is its greatest element, what is its smallest element, or the least element. Yes, if you consider power set of a set What is the greatest element you can make out of this set with intersections and unions? Anyone? And what is that set? That is the power set itself. Very good. And what is the least element in that collection? Yes, excellent. It is 5, right? So basically, power set is thus a bounded lattice. Okay, what about the set of positive integers under this order? Less than. Okay, does this have a least element? If I consider the set of positive integers, okay, does it have a least element? You remember what is least element, right? There you have nothing below it, right? What about greatest element? Do we have a greatest element? No, right? So is this a bounded lattice? It is not, right? Because you have a least element, which is 1, but greatest element does not exist. Okay? So this is known as your bounded lattice. Okay? So this properties we all know. If I take a union with the greatest element, it will give me the element back. If I take the intersection with greatest element, it will give me the set back. These are all the laws we have studied in set theory. So they apply here as well. Okay, the last thing which I want to two things which are left here are the distributive lattice and the complement lattice. Okay, now what is a distributive lattice? Okay, you can see a huge slide here, but this has nothing new. Okay, let me just remove that slide and let me see intuitively. Can you tell me what could be a distributive lattice? Like any wild guess will also tell you what should a distributive lattice be. Okay, first of all, what is a lattice? Lattice is any non-empty set A which satisfies what properties? It satisfies associative, and what all properties does a lattice satisfy, class? Yes, class, it satisfies associative property. We just saw 3 slides back, right? It's commutative, associative, absorption, right? So if I satisfy associative, commutative, absorption, I am a lattice. Okay, now what should a distributive lattice be? And you already know lattice is defined for 2 operations, intersection and union. So what should a distributive lattice be if you don't look at the definition? Exactly. It comes from the name itself. It should satisfy the distributive property. Okay, and what should distribute over what? The intersection should distribute over union, and union should distribute over intersection. That is only thing which we have in distributive lattice. If you consider the distributive property of intersection over union or union over intersection, this should hold. Okay, so any lattice satisfying this property in addition to these 3 properties is known as a distributive lattice. Okay, is this clear, class? I'm going a little fast because I have a meeting at 3:30. Okay, but is this clear? I mean, as I said, the main thing in this is to understand properties. All the new things are just combination of these. Okay, coming on to the last slide now. So the last thing in this module and in this course is what we called as complemented lattice. Okay, let's see what do you mean by a complement. Let us suppose L is our bounded lattice, which means it has a lower bound. Suppose I denote it by O, and it has an upper bound, which I denote by L. Okay, if an element X exists in set L, okay, we say that this element has a complement if you take a union of this element and its complement, it should give you the upper bound. And if you take the intersection of the element with its complement, it should give you the lower bound. Okay, if for all the elements such kind of complement element exists, such a lattice is known as complemented lattice. Okay, let me just repeat what I said. First of all, what we consider is a bounded lattice. Okay, what do I mean by bounded lattice? A lattice is said to be bounded if it has both upper bound, which I denote by L, and a lower bound, right? Like we saw in the last slide. Okay, so I have a upper bound as well as a lower bound defined, right? Now, what is this L? This is actually a set, right? A non-empty set. Now, if an element X in L, okay, for this element, if there exists another element A in L, okay, such that A is called complement of X if the following holds. If I take a union with this complement, it will give me my upper bound. And if I take intersection with this element, it will give me the lower bound. Okay, so such a element is known as complement of that element. Okay, now if this condition holds for all elements X in L, such a lattice is known as complemented lattice. Okay, I'll be sharing a tutorial where I will show you the examples. Okay, so don't worry about that. But is this clear? What do you mean? The overall definition. What do we mean by a complement of an element, and how do we define a complemented lattice? Yes, class. Is that clear? All right. So I would like to just quickly summarize what we studied. We studied these different properties, right? We had closure, we had associative, we had identity, we had inverse, we had commutative. Okay. These two made us semi-group. This made us monoid. These four make group. This all makes abelian group, right? Then we saw what is ring. Okay, ring is that algebraic structure which satisfies all of them for addition, and for multiplication it satisfies just the first two. Okay, then we came to lattice. What is lattice? It is also an algebraic structure defined on a non-empty set, but the operations are union and intersection. So these are set operations. Okay, now what is a lattice? Lattice is something which satisfies the associative, commutative and absorption properties. Okay, if it satisfies all three of them, it is known as a lattice. Okay, now any lattice which has an upper bound and lower bound, that lattice is known as bounded lattice. Okay, so what is a bounded lattice? Which has a well defined greatest and lowest element. Okay, now I'll come to Tanya to complement lattice again. Now, when do we define complemented lattice? For complementary lattice, first important thing is that the lattice should be a bounded lattice. Okay, which means there should be an upper bound and there should be a lower bound for it. Okay, now before I define complemented lattice, I need to define complement of an element. Okay, if I have this lattice defined on non-empty set X, which L, which means it's a set. Okay, it will have a number of elements. Suppose X is one element in L. Okay, we say that there exists an element A which is said to be complement of X if the following holds. If I take their union, it should give me the upper bound. If I take their intersection, it should give me the lower bound. Okay, so that kind of element is known as complement of the element X. Okay, now if element complement of an element exists for all the elements of set L, then such a lattice is known as complemented lattice. Is that clear, Tanya? What is complemented lattice? You are given a lattice and for all its elements their complement exists. Okay, by complement exists I mean these two relationships hold. Okay, such kind of lattice is known as complemented lattice. If there is even a one element in L for which complement does not exist, then you cannot say that's a complemented lattice. Okay, is that clear? Yes, class, is that clear? All right, so I'll stop there.